Good afternoon, everybody. My name's Sarah Hunak, and I'd like to welcome you to another one of our SRP webinars in association with AURPO. Today's topic is Teaching AI the Laws of Physics. As always, before we start, I'll just go through some of the ground rules. The webinar will be recorded and available afterwards on SRP's YouTube channel, so you can watch it back there. You can ask questions, as always, through the Q&A box. You can also vote for other questions that other people have asked, and at the end, the most liked questions will be asked to the presenter first. Any that we don't have time to ask during today's session will be emailed to the presenter and posted for SRP members on our website. If you'd like to claim CPD points for your attendance today, then please email the code to the email address on the screen now. We'll also pop that into the chat box so you can jot that down during the talk. And as always, if you've got any feedback on these webinars, please email them to Charlene. Just need to plug very quickly, joining the SRP if you're not already a member. There are many, many benefits for being a member of the SRP, and all the details of how to join are on our website. We've got a couple more webinars coming up in April. So we've got Nuclear and Exemption Guide on the 16th, and then from X-ray astronomy to portable gamma imaging on the 30th. So if you'd like to log in for those and attend those ones, then you can book via our website. We've also got a new issue of Radiation Protection Today, our magazine, out now. Go check it out. And finally, just like to plug the ERP Congress, which is coming up very soon in June. The exhibition is now sold out. We've got over 600 people booked on to attend, but we do have sponsorship opportunities still available. So if you're interested, then get in touch with Charlene. So now I'll hand over to Ralph, who's from CLEAPS, the AURPO Executive Committee member, who will introduce our speaker for today. Over to you, Ralph.
Oh, thanks, Sarah. Just before I introduce our guest today, I'd like to put our plug in for AURPO. And AURPO is an organisation for those in radiological protection in higher education and research environments, and the odd interloper like me. It's a friendly and professional organisation where members support and help each other in the field of radiological protection. And to plug our annual conference this year, it's at the University of Strathclyde in Glasgow, and it runs from Tuesday 22nd to Wednesday 23rd of September. You can book online at www.aurpo.org.uk. Now it's my pleasure to introduce Dr. Ahmed Aslam. Ahmed is a nuclear physicist and leads the physics and digital technologies team at Armentum. He has more than 30 years of experience delivering and leading major programs in nuclear physics and digital technologies, with a particular focus on the convergence of the two domains. In addition to his industry role, Ahmed is a lecturer in nuclear technology at the University of Manchester, where he contributes to the education and development of the next generation of nuclear professionals. Ahmed is also a member of the steering board for the Nuclear Institute's AI4 nuclear programme, where the remit includes supporting the nuclear industry in the adoption of novel AI technologies, aligning sector activities with the UK National AI Strategy, and addressing the technical, regulatory and cultural changes associated with deploying AI in the nuclear sector. So Ahmed, I'm looking very much forward to this, and over to you.
Thank you very much indeed, Ralph, and Sarah and Charlene working in the background there. I'll share my screen. Okay. Well, it's absolutely fantastic to be back here at SRP presenting again. It's my favorite community. So the presentation today is about teaching AI the laws of physics, or how we can leverage AI to learn physics and obey those laws. So without further ado, let's get cracking. Now, Ralph has explained all about me, so I'll not dwell too much on this particular slide, but I lead the physics and digital technologies team at Armentum, and you have my contact details in the email in case anyone wants to email after the presentation. Now, just want to quickly run through what this presentation is about. So I'm going to start with a short slide summarizing what this presentation is going to cover. And I'll start with a physics-informed AI example. It's a real-life one, showing what's actually possible with this sort of technology. I'll also cover classical versus neural physics solvers. Now, neural physics is a physics-informed AI, but we normally solve our problems, physics problems, using classical codes. And I'll just compare the two and then summarize how we can use AI instead of our classical codes for numerical problem solving, and why we need to at all. I will then set down a few real-world challenges. These are complex physics challenges that really can't be solved with traditional numerical codes. And then lead into, I'm sure we all know about laws of physics, but I'll have a slide on what the laws of physics are and how they relate to being embedded into neural networks. So I'll explain a little bit about neural network architecture and how we can then change that to actually embed some of these physics inside, and the results, as you will see, are quite startling. I'll also say a little bit about building trust. If we are going to be using this technology going forward, we have to have the utmost trust in the answers it produces. So I'll cover a little bit of that, but then head straight into examples of what is possible, generally in physics, but especially in radiation protection and medical physics and so on. So I've tried to keep this presentation really at a high non-technical level, but I may have failed. So certainly in places, so apologies in advance. So this presentation is about how we constrain AI with physics, rather than asking it to infer physics implicitly from data. So what are we going to get from this presentation? Well, you'll see that what teaching physics actually looks like in practice, how mathematical equations become constraints that shape the solution. We'll connect this to radiation protection outcomes, faster and more robust modeling in situations where time really matters, but the data is very limited. So with that framing, here's the path we're going to follow. I'll start with a quick real-world example. And you may well have kind of come across this on social media, on YouTube. This was recently took place in China at the Spring Gala Festival. This is physics-informed AI in action, believe it or not. So what you're seeing is robots that leverage physics-informed AI to bridge the gap between digital animation and real-world stability. This ensures that even highly complex creative movements remain physically viable. Did that stop it? Now they use a physics engine, and I think I say e.g., I'm pretty sure it actually is NVIDIA Newton. That integrates physical laws like gravity, friction, inertia, and so on, directly into the AI's decision-making. It's a closed loop design. So AI control allows them to react to each other and adjust their balance, as well as spacing, timing on the fly. And they can even compensate for uneven surfaces, lighting-induced sensor noise, and whatever. It can also handle unpredictable environments, relying mostly on real-time feedback from high-torque electric sort of actuators. So the fluid, as you can see, is like the movement is very fluid and human-like across more than 23 joints simultaneously. And they're trained by observing human dancers, but they will only accept, they know what their limitations are. They will only accept the movements that are consistent with the laws of physics and mechanical constraints. So as you can see, we've come a long way from the Doctor Who type of robots. So how is this relevant to this presentation? Well, the technology I'm about to describe to you is exactly this. It's the applications are vast in every area of our lives, and science and engineering in particular. So before I describe how we can incorporate physics into AI and AI in general, I think it's worth comparing the classical codes with the newer neural physics solvers that use AI. Now, analytical solutions are quite difficult to obtain for very complex systems. Now, these are where we've got very high dimensional data, multimodal. We might have all kinds of images, videos, and data mixed, multi-resolution, so on. So once you have complex data, solutions are not very easy to find. Now, we have codes like based on, say, finite element methods, mesh-free methods, finite difference methods. They generally give good answers, but they struggle to model complex systems, e.g. where we have coupled radiation, thermal, chemical, and mechanical effects. And they can take from hours to days and even weeks on high-performance computers. Whereas physics-informed AI solvers use AI deep learning to solve the equations. So they don't, as we'll see in the later slides, they don't actually solve numerically in the same sense, but they still solve the same equations, unlike the traditional methods that really get bogged down in numerical solving of the equations. So why should we use AI for numerical problem solving then? Well, our traditional classical solvers, and I've used them for most of my working life, and they've really served us well for the past 50 years, but they can struggle with modern demands for rapid solutions to complex problems. They generally are very cumbersome, thousands of lines of codes that were written many decades ago, and gradually it might have been kind of upgraded and so on, using later versions of the code. So you have a mismatch. They are not very neat in the way that they have evolved, although they still work, and they require considerable computing resources. But above all, in this modern world we're living in the age of digital twins, we require real-time answers. And some of the traditional or classical codes, if you like, are unable to do that, even if they can actually solve the problem. So Now we turn to physics-informed AI. So what can that do? Well, it can utilize the very powerful fitting capabilities that are actually part of the neural network architecture. And we can use that to actually make the neural network learn the rules behind the data and physical equations themselves. It'll become a little clearer in the following slides. But we can train them to solve those very same equations that are incorporated into existing codes. And as I've said, it's the fact that we are able to make use of the existing infrastructure means a lot of the code, a lot of the solving is actually done within the neural network itself. So we simply embed the equations and give it a few short rules, say do this, do that. But a lot of the solving is actually done within the AI infrastructure, which means it's a much shorter code. Typically, maybe for a complex problem, maybe 100 lines, 200 lines tops. And we do get real-time answers, miraculously. I think it's also worth looking at some of the very complex computational challenges that face the nuclear industry. And of course, all industries face problems, but I'll just focus on a couple of mine, the ones that I've been working on over the years. First one's on Fukushima fuel debris retrieval. Now, many of you will know that there was a tsunami 2011 in Japan that took out multiple reactors at Fukushima. Now, the situation we have is that we've got a severe core meltdown on multiple cores. So as I've sort of written here, we have a dangerous cocktail of nuclear fuel, melted sort of structures, all kinds of things in sort of unknown configuration, very highly heterogeneous. So you have solid blocks, porous crusts, and particulates and so on. They typically exhibit non-Newtonian behavior. And you have solid liquid gas interactions. And you've got the problem of resuspension, sedimentation, and aggregation. All of these effects are very difficult to capture simultaneously with traditional codes. And you add to the mix the fact that there's very little experimental data. Then you're pushed into a corner. There's nowhere to go. I know we've been trying for 15 years to model something like that, and I've not succeeded. The next example, by the way, the images there are not real, ironically generated by AI. So the first generation Magnox storage ponds and the pile fuel storage pond, against a different problem to Fukushima, but has some similarities. We have degraded Magnox fuel, corroded metals, graphites. In fact, all kinds of materials are dumped in there for some reason. And they range from really very small micron scale up to millimeter scale, up to larger sort of items. And because of the radiation environment, the radiolysis leads to changes in density, gas generation, and so on, and various rheological properties. It is very poorly characterized. It's not very easy to pin down exactly what you have. And again, as with Fukushima, there's very little experimental data to go on. So the current computational tools are limited in what they can model, especially when there is very little experimental evidence. So before we head into the physics-informed and neural networks, just a little bit on the laws of physics. Now, the laws of physics describe how matter and energy behave in the universe, and they underpin everything from everyday activities to advanced technologies. And these laws are typically formulated as differential or partial differential equations. Now, these range from Newton's laws of motion, conservation laws, laws of thermodynamics, through to quantum mechanics. Together, they form the foundation of modern science and technology. They are continuously tested and refined to improve our understanding of reality. AI can make informed decisions knowing the laws of physics. I know we have complained up to now, AI is hallucinating, is giving the wrong answer, you name it. It's fantastic when it does work. But because we haven't taught it the intelligence, it's not surprising that it can get it wrong. So when traditional computational methods struggle, we can leverage the advances in AI to solve those equations much more quickly and much more efficiently. Neural networks, then. This is a convolutional neural network and works like almost like an assembly line that compares input data. For example, it might be an image, and it's been prior trained on lots of images, and you feed the image that you want to classify into the neural networks. It will split that up into multiple shorter images and feed them into what these are called neurons. They're nothing more than just mini calculators. So these flashing on and off actually represent the degree to which that part of the image, let's say, agrees with the one that it's being trained on. So flashing on and off, once they come to a decision, they pass that on to the next layer of neurons who progressively build up an image until the output layer, which says, yes, I have made my prediction. This is an image of a house or a car or a fish, whatever that might be. And it then compares that to the value that it's been trained on. And if there's a discrepancy, it's sort of actually set down in this loss function, which means ideally the loss function would be 0. In other words, the prediction will exactly match the true value, but that will very rarely happen. There is a small discrepancy, come what may, but you want to kind of send it back until this is small enough. So in the backward propagation, the neural network is asked to essentially, could you take another look, please? You're not quite there. And it repeats all of this again and says, am I closer this time? And then they compare, and if the loss is acceptable, then we say we have a solution. And then there you've got your prediction. There's no real intelligence behind the decision making. these are just mathematical operations, pattern matching. And the predictions are only as good as the training data itself. So the basic AI is used in fields like computer vision, natural language processing, and general pattern recognition. No doubt, you know, we all use ChatGPT and Gemini and so on. And it's very good, and it's got very good. Recently, I went through the airport, and my passport has my picture, which doesn't have my beard on it. And I thought, oh, is it going to recognize? Of course, it's AI systems. But sure enough, within a split second, it recognized me. I said, no problem. Had I sort of transformed myself into Gandalf, maybe it might have struggled. But, you know, the AI has got very good at recognizing patterns, people, car number plates, you name it. And this is how it actually kind of works typically. So forward propagation to make a prediction and backward propagation to reduce the loss function. In other words, you keep going round the loop, changing your prediction until the predictions match the real trained data. So it's learned purely from data. And needless to say, it requires large amounts of high quality data. But it does struggle to predict anything outside of that range of training data. So the disadvantages are that it's also computationally very intensive. It uses so much computing power that this is unbelievable. And there's also this black box nature and the lack of explainability. I mean, how does it come up with a particular decision? Well, we don't really know. We've got these neurons firing and passing data from one point to another, and no one really knows how it actually converges to a solution. And of course, if there are any biases within the data, then they get also amplified in this process. And there is genuine lack of true human creativity in there. So we now move to physics-informed AI. So just a quick intro to what this means. So when you hear physics, AI for physics, you might think it's just one thing. It's not. We have many different forms of AI physics, or where we can teach physics to AI. Now, on the left here, we have data-driven machine learning, and that learns patterns from just purely from data, but has very little understanding outside of that realm. Now, the reason why I put some of these images on is it's like a young baby learning to balance and walk, pick up things. All of these things, they really have no understanding as such, but they just learn by observing. So it's like that. Now, in the middle, we have physics-informed neural networks, which we call PINs. Now, they learn from physics, and we explicitly constrain the solution with physics partial differential equations. Now, what that means in practice in this level is that the actual equations themselves may not be embedded in the neural networks, but we force the answer that the neural network comes up with to comply with certain constraints. And it might be that we have constraints on, let's say, pressure or temperature or velocity, whatever the physical parameter might be. If we know the constraints on that, we can build that in. And because they are physics constraints, that will mean that that's a physics-informed neural network. Now, on the right-hand side, we've got neural physics approaches such as AI for PDEs. This is AI for partial differential equations, where we express the discretized PDE solvers inside the machine learning frameworks, inside the libraries. So the solvers are actually embedded inside the neural networks. And it does not require any training because it's solving, just purely solving those equations. And this is where, we have a deep understanding of the physics and the problem, and we know how to come to a solution. Now, neural physics is a very new kind of science. So I wanted to put this slide up for you. It's part of AI for science. And if you look at neural physics, this is about trying to embed or teach the physics by the way of actual equations that we know inside neural networks without the need for training. And this area is actually recognized as one of the most important developments of the 21st century. This problem you see here has been solved by the neural networks. It's a flow problem, courtesy of Imperial College. It's been done by a world-leading team led by Professor Chris Payne at Imperial College. I urge you to check them out. They're absolutely fantastic at what they're doing with this kind of technology. I've got one or two more examples later on this. So how do we inject physics into AI? So I consider here two forms of pins. One in which we train the neural network on high quality data. Now that might be based on existing physics codes, or it might be very high quality experimental data, whatever that might be. And on the right-hand side, we've got physics-based or equation-based neural network. Now, this actually embeds the equations into the neural network. So how does this work then? Well, the first part of it is as kind of normal neural network. It takes the input data, compares with the training data and gives an output and says, does it agree or doesn't it agree? But at that point, we pass that output onto this part of the neural network, which says, hang on, does this output also obey the laws of physics? Does it, or does this parameter, for example, it might be pressure or temperature, is this changing or behaving in the way that is consistent with this equation that we have? So it gives it an extra layer. Now, if the answer is no, we send that back and say, well, go and give it another try. Now, this model here together is very robust because it will match data and it will respect the physics equations as well. And not only can it do forward problem, come up with an answer, but it can also work backwards, inverse problems, where it can infer unknown parameters from observed data, really. The reason why we're able to do that is because these derivatives are actually computed automatically by the neural network. And we simply use them. And we say, well, is the rate of change of this parameter or that parameter consistent with the physical equation? If not, let's send it back. And that's, in essence, how we embed the laws of physics. Now, implementing them is not as simple as one might think. Whilst, we can define the equations very accurately and embed them, we are ultimately dealing with a neural network architecture that has a mind of its own, in a sense, with lots and lots of calculations are happening and interchange of information. It can solve, once you embed the physics, it can solve any problem that you can express as a physics equation. So if you know the laws of physics, and so you will know the equations, be it radiation transport, fluid dynamics, heat transfer, whatever that might be. If you embed them in, then it learns very quickly. And the answer comes back not in hours or days, but in milliseconds or even less. Of course, there are some challenges. The optimization is not easy. The hyperparameters, as we call them, and these are number of layers, neurons per layer, how to set the learning rate, how to deal with very sharp gradients and discontinuities, shock waves, things like that, means it is a tricky optimization. But above all, I think it needs very knowledgeable people in AI and domain experts, so knowledge of physics and materials science and whatever discipline, and numerical methods. So that's not easy. Ultimately, in order for this AI sort of numerical solvers to become accepted, they need to be trusted. Now, for that, we can basically split this into several elements here. Verification. Are we solving the equations correctly and implementing the method as intended? And in validation, do the model outputs match reality in the scenarios that we care about? And then there's uncertainty. We must quantify and communicate uncertainty, especially near decision thresholds, so we don't create false confidence. So we have to align with appropriate frameworks, like the NIST standards framework and the risk management framework and so on. So it's only by following these steps that we validate our AI code and make it acceptable in the eyes of the regulator and the users. I'm just going to now turn to some examples of this technology. Now, this one is a on a discrete grid, but it's totally been solved on AI for PDE framework on a GPU computer. And you can see that this is, I mean, this particular one is no big deal. You can actually solve this using other numerical codes. But this is giving a real-time solution. So you can see the solution as it's developing. And here we have another example of a sort of velocity distribution of cubes, stress distribution. Again, you're getting real-time answers very, very quickly, but the answers are the same as they would be with a normal code. This is a much larger example, again, from Imperial College. Now, this is on a 32 kilometer by 32 kilometer area of London with over 200 billion nodes, and it's tracking airflow around there. I think it was done around the time of COVID. But the speed you get is not only real time, it's actually 100 times faster than real time speed. That's the key difference with something like AI as opposed to, you know, your classical solvers. If I now turn to some radiation protection specific examples quickly. So for a typical, say, facility shielding design, the current limitations are that we rely on empirical build-up factors, conservative assumptions. The geometries can be complex with penetration, sky shine, masers, and so on, that typically rely on Monte Carlo solutions. But with physics AI enhancement, we can embed real-time neural solvers for radiation transport equation. So what is the impact of that? Well, rapid optimization of bunker wall thickness, for example, real-time dose mapping for redesigns, and inverse shielding design, where we can optimize material placement to meet certain dose limits. Another one, radiation detector optimization. That involves solving the charge transport equations, and we can embed them using physics AI into the neural networks. The result is that we have rapid contamination prediction, dynamic evacuation zoning, if that's what you're designing, and real-time risk maps. These developments have already shown beyond proof of concept. Emergency response and environmental dispersion, another one where we have advection diffusion equations. And once you embed them into physics AI and train them appropriately, the end result is that you have a rapid contamination prediction, and again, dynamic evacuation zoning, and you would get real-time data on the radiation dispersion, therefore allowing you to quantify the risks and map them. General shielding design. Now, this is an example from Oak Ridge National Laboratory. Typically when designing a nuclear fuel cask, the considerations are that it needs to be light, but it needs to provide adequate shielding. So the standard simulations, say, using codes like McBen, MCNP, they actually take too long because there's an optimization loop that you have to go through with combinations of various thicknesses of steel, lead, polythene, and so on. But what Oak Ridge, in this case, have done is embed the physics inside the neural networks, the governing equations. This is on a digital twin of a radiotherapy system. Hopefully I can share these slides with you so that you just get an idea of what this technology is capable of. Now, with something like this, we can continuously re-optimize the treatment and a closed loop sort of radiotherapy control, where we can get real-time control and personalized radiation protection. Similarly, with radiobiological modeling coupled to dose PDEs, and the impact of physics-informed AI is that the biologically adaptive radiotherapy regime is possible, and dose painting guided by mechanistic multiphysics modeling. So just want to wrap up quickly, just by asking a few questions, which no doubt you'll be asking as well. Will physics AI-based methods replace traditional codes? Well, eventually they probably will, but in the short term, it's unlikely. And that is because the current codes are validated and accepted. And where, of course, the nuclear industry, we don't like taking on new things easily. It will, in this case, it's my best guess that the medical sort of area will be the first to be using and taking up such a technology as it is right now. Training pins is, as I've said, difficult as well. The validation is mostly empirical because there's no rigorous universal neural network convergence theory yet that has been developed. But it's fair to say that codes that do not adapt to incorporate the latest AI advancement do risk obsolescence. We can take advantage of AI solvers alongside our existing codes and make hybrid codes to give us best of both worlds. And the very final slide then on the ethics of super intelligent AI. And we talked about the intelligence and how we can build now the laws of physics and all of the other sort of data that makes neural network almost self-aware. And I've not even mentioned the Q word, quantum physics. With the advent of quantum physics, which is upon us, and a new field is developing called quantum physics-informed neural networks. That is making for a super intelligent AI. In fact, it won't be long before we drop the word A, as in artificial intelligence, and call it non-biological intelligence. So the questions are, will future AI possibly exceed human intelligence? Quite possibly. And can it make decisions better than humans in governance, military, economics, industry, and medicine, and all the other fields? In some ways, that's happening now. Can humans coexist with superior non-biological intelligence? Well, it remains to be seen. And will the control be assumed by a few corporations or states, bringing massive inequality and destruction? We're well on the way to that, by the way. And will humans lose control altogether of the technology? Again, that's a real possibility. I think it's a problem too big for a single group or a nation to handle. I think the entire humanity needs to come together. And we need to ensure that superintelligence works for the benefit of humans and the environment remains aligned with basic human rights and values, and it does not end up in the hands of only a few groups or nations for them to misuse. So I'll leave you with that thought. Now I'm going to have to flick through this quickly.